So yes, class, in the last class we had started with nuclei. So first thing that we had seen was the basic terminologies. What are nucleons? Nucleons were simply sum of protons and neutrons. Then atomic number we had seen, mass number that was represented by capital A, and atomic number that was represented by Z. So capital Z that represented the number of protons or the number of electrons that are present. All right. Now, after this, we had seen the nuclear size that had this relation R is equal to R naught A to the power 1 by 3, where R naught was a constant, 1.2 Fermi meter was given. Usually, you take R naught if nothing is mentioned as 1.2 only. If something is mentioned to you, then use that value. Otherwise, using 1.2 Fermi is fine. Then we had seen that nuclear density, when we put all the formulas for all the values that are present for nuclear density, we obtain this value 2.3 into 10 to the power 17 kg per meter cube. This shows that nuclear density is independent of the mass number. A, you do not have in your answer or anything else. So any other material you have, any other medium you have, your answer will be the same for nuclear density. Let us practice 2 to 3 questions, then we'll move on to binding energy. So in this question, germanium is given. Germanium, so A, mass number is given as 70. So R was equal to R naught A to the power 1 by 3. So R will be R naught is 1.1 Fermi meter, and A is given in the question 70. You can look at the symbol. Chemical representation also we had done in the last class. So this is 70 to the power A by 3. 70 to the A power, see, 4 into 4 is 64, no? So it would be 4, it is around 4.12. So this will be around 4.12. That will be 4.53 per meter. I'm writing one more question. By the time, just note it down. See, one more relation was given that I didn't mention, Einstein's mass energy equivalence, which you had seen in dual nature. So actually we have seen this formula in dual nature. That's why I'm not repeating it. Just a question came. So let us just see. E is equal to mc square, we know. Mass is given as 16 milligram, that is 10 to the power minus 3 kg. C is speed of light, 3 into 10 to the power 8 meter per second. So energy is 16 into 10 to the power minus 3. Speed is 3 into 10 to the power 8 whole square. So see, when you solve this, you will get your answer in joules. If you want, you can divide it by 1.6 into 10 to the power minus 90. You will obtain the answer in electron. Fine, note down these 2 questions. One more question, I'll write it down. See class, such questions can also be given to you. Assuming protons and neutrons have equal masses, how many times nuclear matter is denser than water? So it means density of the nucleus, nucleon basically. And then you have nuclear density, you have to have one side, and then you have to have density of water. So see, nuclear density we have calculated in the last class. Nuclear density was 2.307. 2.3, let's take it, into 10 to the power 17 kg per meter cube. And you know density of water. What is density of water in SI unit? Density of water. Yes, what is the density of water? Yes, Memuna, what is the density of water? Are you present in the class?
Yes, teacher.
So what is the density of water? In SI unit, CGS unit, in any unit, tell me. Sneha. So Memuna does not know the density of water. Sneha, what about you? Yes, correct. Sneha, Salman, correct. Salman, that is in CGS unit. Sneha has answered in SI unit. So we take it as 1000. Those who do not know, remember it right now. 1000 kg per meter cube. That is the SI unit of water. See, Memona, this won't be mentioned to you in the examination. Density of water. So please remember this value. Density of water, no, this won't be mentioned to you in the exam for many questions. Okay, so remember, just remember this value. And in CGS unit, that is 1 gram per ml. So yes, if we take the ratio, 2.3 into 10 to the power 17 by 10 to the power 3. So your answer will be 2.3 into 10 to the power 14, and units will get cancelled. So density of water, how many times nuclear matter is denser than water? So it is this much amount of times denser than it. Then you can make the comparison. Note down this one as well. Okay, class. Please try this question and send me the answer in the solution in the chat box. Nuclear mass is given to you as 55.85 AMU. Now, iron is given to you. Iron's atomic mass is also given. Mass number is also given. Every data you have, quickly within 2 minutes, try to answer this question, nuclear density. Yes, answer. All of you answer quickly. Khalid, Memuna, Salman, Sneha. Answer this fourth question. Yes, Khalid, what is your answer coming? Okay, you have answered. Khalid has answered. Apart from Khalid, Khalid, your answer is absolutely correct. Memuna, any answers that you've got? Salman, what about you? Sneha,
Yeah, yes, ma'am.
answers? Okay, last 1 minute. See, class, you don't need to perform any calculations in this. What did I tell you? Nuclear density is fixed. It is independent of mass number. Whether it is for iron, whether it is for beryllium, everything we had calculated initially only. So it will come around 2.9 into 10 to the power 17 by exact calculation. But even if you do not calculate, you can easily write your answer 2.3 into 10 to the power 17 kg per meter cube. This is the exact answer. Fine. Next topic that you have in nuclei is binding energy and mass defect. But before that, firstly, let's do just mass defect. Mass defect. Now see, mass defect is basically difference between the rest mass of nucleus and I'll tell you. Rest mass of nucleus means mass of proton. This is the mass of proton multiplied by atomic number. Complete amount of protons. Fine. How many neutrons will be there? This is protons. What about neutrons? That will be A minus Z, number of neutrons into mass of neutrons, total mass of neutrons. This is total mass of protons. This is total mass of neutrons. Fine. And then complete mass of the nucleus, let's say this is M. Mx you can say, or M you can say. Total mass of nucleus. So mass defect is basically sum of the rest masses of the constituents of nucleus, that is protons plus neutrons. So that makes ZMP plus A minus ZMN minus means difference between this entire term and the mass of the nucleus. This is known as mass defect. This is known as mass defect. If you divide it by mass number, you get mass defect per nucleon, which you must have studied in your chemistry. Do you have that lesson solid state there? You must have had packing fraction, this term. I don't know if it is there in your syllabus or not now. But packing fraction is basically mass defect per nucleus, per nucleon only. That includes your, if you divide this entire term by A, mass number. Now then, what is binding energy? E is equal to mc square, you know. If this M becomes mass defect, that energy is known as binding energy. Clear? E is equal to mc square is valid for any other particle as well. But as soon as this mass becomes specifically mass defect, then you say this is what? This is binding energy. This energy, we name this energy as binding energy. So binding energy, we call it as delta mc square. Definition of binding energy, you'll find it in the notes that you can refer later on. All right. So this is the energy. But what is meant by this energy? It is the energy that is required to break up the nucleus into its constituent protons, neutrons, and to separate them at such a large distance, that they should not be able to meet each other. This energy is actually, this is the binding energy, and the formula is this. Same definition is there in the notes that you'll find it there. So binding energy, you can simply say energy that is required to break up nucleus into its constituting parts. Binding energy required, whatever thing was binded to break up the things that were bound together. All right. So it means if you put this, the formula of binding energy, this entire term of mass defect, that is ZMP plus A minus ZMN minus mass of the whole nucleus. This is mass defect into C square. In this, you will get your complete answer in joules. This is how you get your complete answer in joules. Understood? Like this, you solve your answer. Clear? So mass defect is this, binding energy is this. If you want to find out binding energy per nucleon, binding energy per nucleon, then divide the binding energy simply by the mass number. Now, how is it dependent on mass number? That I'll tell you. First, note down all these points, then there's a curve that I'll tell you that shows how it is dependent on the mass number. Note down these few points. One more thing, class, one more thing. See here, when you will calculate delta M, let's say some value of delta M you will get, that is the mass defect. Delta M is the mass defect. And then you will put C square. C square is speed of light whole square. C is the speed of light here. Then first you will put 3 into 10 to the power 8 meter per second whole square. And then if you want to convert it into electron volt, you will convert the entire term by dividing it by 1.6 into 10 to the power minus 19. Rather than, no, we usually have the binding energy per nucleon in mega electron volt. And to obtain this unit, just multiply mass defect by 931 and you will get your answer in mega electron volt. Just note it down somewhere in your note. I'll do a question with you. Let's do a numerical first, and then we'll do that curve. Let me do a numerical so that this gets clear. First, note this down, and we'll do a numerical. See, here in this question, you have to calculate binding energy per nucleon of calcium. Calcium's mass is also, just a second. One more thing is given in the question. That is mass of the atom, mass of calcium atom. So that is given as 39.962589 am. We take it now as 40. So actual mass is given. So in this lesson, you will be having all the masses like this. That's why a little more of calculation, but rest of this thing is fine. Now see, how many protons are there? 20 protons. So remember ZMP plus A minus Z Mn minus M of the atom. We have to solve this, then multiply it by C square. That gives binding energy. And we have to divide it, this entire term, by A to get binding energy per nucleon. Now let us substitute one by one. Mass of proton. See, mass of 20 protons. You have 20 protons. So mass of 20 protons will be 20 into 1.007825. So that will be around 20.1565 AMU. So this is ZMP we have calculated. Then mass of neutron we have. So 40 minus 20, that is 20. So mass of 20 neutrons. Mass of 20 neutrons, that will be again 20 into, how much is given? 1.00865. 8665. So this will be around 40, no, this will be around 20.1733. 20.1733 AMU. So ZMP you have, and this entire term, this is basically ZMP, right? Z into MP, this is Z, this is MP. And this entire term is A minus Z. See, this is A minus Z. This is MN. Till here we have solved. So add it, see what till here, what are you getting? If you add it, you will get 40.3298 AMU. Now what do we have to subtract? We have to subtract the mass of calcium atom. Mass of calcium atom is given as 39 point something. Look here, 39.962589. So from this term, subtract mass of calcium. Mass of calcium nucleus we subtract. So when you will subtract how much? 39.962589. You will have your final answer as 0.367211 AMU. So this is what? This term is finally the mass defect. And the same formula we have calculated. So you have delta M's value. Now binding energy, I have told you multiply C square with it. It's better just multiply 931 mega electron volt. So this will be 0.367211 into 931. So this will give you 341.87 mega electron volt. This is mega electron volt. All right. This is your binding energy. But we have to find it binding energy per nucleon. So nucleon, you know, per nucleon is 40. Number of protons plus neutrons, that is complete atomic number, complete mass number. Mass number is 40. So binding energy per nucleon, this will be binding energy by mass number. So 341.87 by 40, that will give you 8.547 mega electron volt. This becomes your answer. I hope you've understood. Clear or not? At any step, clear? Okay. At any step, if you get stuck, let me know. Note down this question. Step by step, you can solve this question. I think you all have written, no? Note it down. Then one curve we have to do.
Ma'am, can you share the question also, please?
All right. Now see, there are certain binding energies per nucleon's value given in mega electron volt along this graph. There are certain values like 0, then you have 2, then you have 4, 6, 8, and so on. And here also in this graph, you have mass numbers like 50 at a point, 100, 150, and so on. But how the graph is shown is, firstly, for hydrogen and helium like atoms, it is directly increasing. Means mass number is remaining constant, but the binding energy is increasing. All right. Then it increases furthermore, and there's a sharp dip. This is helium. Here you have hydrogen, both the isotopes. There's a dip you observe for lithium, then it again increases for carbon, then it again decreases for nitrogen, then it again increases for oxygen. And so then it increases for sulfur linearly proportional with the mass number. As the mass number increases, and now the binding energy is increasing. But at this point only, which is iron, which is exactly around 50. If you look at, this is around 50 something, this is iron. And then you have continuous straight graph like this. Some elements are kept here, some elements are here, some elements are here, like this you have it. Now, binding energy basically tells you that it is a measure of stability of the nucleus. So, how much greater binding energy is, that will tell you how much stable a nucleus is. So, greater is the binding energy per nucleus, per nucleon of a nucleus, more stable is electron. More stable is the nucleus. Now, see, some important features are like these are nearly smooth curves for helium, carbon, oxygen. Can you see? Quite smooth curves till here at this particular point. Linear, you can say, direct, sharp edges they have. But for hydrogen, all the isotopes of hydrogen, you can see there's a small variation only. It is almost straight, right? So it means hydrogen, carbon, oxygen, all these atoms have high stability. They are highly stable. Nuclei are highly stable of these. But then you look at these lithium, nitrogen. Here you have boron. All these have low binding energy. So low binding energy, that will correspond to lower stability. So lithium, nitrogen, these have lower stability, while the carbon, oxygen, like these atoms, have higher stability. Fine. Then you have a very peak value of 8.8 mega electron volt here, 8.8 mega electron volt per nucleon for iron, that is 56 element. Mass number is from 40 to 120. So this value you have to remember. Apart from this, then you can see as the mass number increases further, you can see the binding energy is gradually decreasing. This is what is it all about, fine? Then you have processes like nuclear fission, nuclear fusion, but now radioactivity is not part of your syllabus. First, tell me, this energy curve is clear? Rest of the details, no, whatever I have said, that you'll find it in your notes, that you can see and study from your notes only. Clear? Don't write it down, don't draw it. This you can easily, you will be able to find it in the notes, fine? So are you clear with this lesson? Can we move on to semiconductors now?
Yes, teacher.
Okay, then let's start with semiconductors if you don't have any issues in nuclei. See, in semiconductors, so before exactly starting with semiconductors, you should have an idea of the classification of solids. How are solids classified? So see, there are certain differences on the basis of which conductors, semiconductors, and insulators are classified. Firstly is based on resistivity. Conductors have low resistivity. Fine, let us just talk about conductors first. Conductors have low resistivity of conductor, but they have high conductivity. Means resistance they'll offer less, quite less resistance will be offered by them. But when it comes to conductivity, they have high amount of conductivity with them. They possess good amount of conductivity within them. But when you talk about resistivity, you will be able to find it very, very low resistivity. You will be able to observe. Fine. So on these are just basis of electrical properties, this classification that I'm telling you. And there are certain values also. Values are written in the notes. So if you wish, you can remember. Otherwise, just remember high or low. All right. So high conductivity. Sigma C. High conductivity. But when you come to semiconductors, see semiconductors, you must have heard of silicon, germanium. These are mainly two examples given in your book, in your textbook. These have low resistivity. While the insulators, no insulators that are present, insulators have high resistivity, exactly opposite to that of conductors. High resistivity. Resistivity of insulators, this is high, but they have low conductivity. That is sigma I, this is low. Now, what about semiconductors? They have everything intermediate in between of these. It means density, resistivity of this is low, conductor. Conductivity, resistivity, we have studied all these terms: resistance, conductance, resistivity, conductivity in current electricity. All these parts we have covered in current electricity. Still, we'll revise it, no issues. So density, resistivity of conductors is low. Resistivity of insulators are high. But semiconductors have resistivity in between them. Same thing goes for conductivity. Sigma C is greatest. Sigma I is lowest. But sigma S is in between of it. So understood. So excessive, and one more thing, one question that comes in one marker is, why is there, if semiconductors have everything intermediate in between, right? If everything is in between, then why do semiconductors have so much usage in industries? Conductors should be used or insulators should be used. Semiconductors should not have any existence. This is just because of one thing, that they have the ability to control current. They have a very good ability to control current. That's why they are used. Otherwise, they wouldn't have been used. Let me write down this statement. Excessive use of semiconductors note down this page.
Ma'am, can you scroll up? Done.
Now you have energy band level theories. Fine, energy band gap theory. You have to classify metals, elements. So to classify solids on the basis of electrical properties, we used the phenomena and the properties of resistivity and conductivity. Right. Second classification involves how to differentiate between these. So second involves to differentiate between insulators, semiconductors, and conductors is using energy level theory, energy band gap theory. So here in this, energy bands are basically two bands you have. Two energy bands you have. One is known as valence band, second bands are known as conduction bands. So conduction bands and valence bands, these are basically bands that are closely spaced energy levels. So what are these conduction and valence band? See, let me tell you, let me draw the diagram. See, conduction band, let me tell you. Conduction band is basically that conduction bands have free electrons that are present. And there are valence band where the valence electrons are present. Now, these valence electrons are not free. They are bounded electrons. These electrons that are present. These valence electrons, these are bounded. They are not available for conduction. They are valence electrons. They are valence electrons. They are completely bound. All right. Then there is a certain energy gap between these two. This gap is known as energy gap. This is the valence band and this is the conduction band. So when sufficient energy is struck upon, whenever sufficient energy is struck upon the valence band, valence electrons transfer from the valence band to the conduction band and become available for conduction. So conduction band have electrons which are free electrons. These electrons are free. They are available for conduction to occur. Understood? This gap that we get is known as energy gap. And based on certain properties of this energy gap, we'll be having, you can simply say valence bond model also. This is also known as valence bond model. Fine. So on the basis of band theory, you just understand this fact that from the valence band, electrons move on and go to the highest energy level, that is the conduction band, where it contributes to the conduction to occur. So this energy that you get, this is lowest energy level. See, these are all energy level. First energy level, your second energy level, third energy level, like this. So this one, the first one that you're able to observe, this is the lowest energy level. Lowest level of energy of conduction band. And this one, this seal, likewise, here also there will be like these energy states. So this one, this is top energy level of valence. Top energy level of valence band. So, okay, I've written the things also here. So they have free electrons and the electrons in the conduction band contribute to current. So these are free. So they'll ultimately contribute to current and conductivity. Valence band have bonded electrons. They do not contribute to current, and energy gap is basically difference between these bands. Now coming, how will you classify or differentiate between insulators, semiconductors on the basis of band theory? So just understand for conductor ones, rest of it will be easier to understand. See, let's say this is conduction band. So conduction band in case of conductors, this is partially filled with electrons. This is partly filled. Partly filled electrons it has. And you have on one hand the valence band. Valence band is completely filled with electrons. And then here you will obtain the energy gap. Energy gap is present. Either this is possible or one more thing is possible, that is the conduction band. This is the conduction band, right? With partly filled electrons. And you have the valence band which are overlapping. So valence band and conduction band are overlapping. If you see such a case, these bands overlap at this particular point. Here, bands overlap. So if you see such a case, this means your conduction, your material is a conductor. So conduction band is partly filled. Conduction band is partly filled. Conduction band. And valence band is fully filled. If you see such a case, it means the element, the material is a conductor. Fine. Now see, then what about insulators? Conductors are very simple. Band gap should be there. Means conduction and valence band should have a gap or they should overlap. Let's talk about insulators. In insulators, this conduction band is totally empty. No electron present. No electron is present. And what about the valence band? Valence band is completely filled with electrons. This is completely filled with electrons. These have all the electrons present. But when there is a sufficient energy within this energy gap that you see, if the energy gap exceeds 3 electron volt, energy gap should be greater than 3 electron volt. Then the electron ejects itself and moves to conduction band and conduction occur. It means this energy gap is what? The energy gap is large. For example, here, okay, I've written the things. Conduction band is empty. Valence band is filled with electrons. Energy band gap is large, that is greater than 3 electron volt. One very good example is diamond. Diamonds, see, the energy gap for diamond is 6 electron volt. So you can easily identify if it is greater than 6 electron volt, that means if this diamond is definitely an insulator. Now, this you can differentiate, that yes, conduction band was partly filled in case of conductors and conduction band is completely filled in case of insulators, so you can differentiate. But now how will you differentiate semiconductors then? See, for semiconductors, no, conduction band is still empty. Valence band has fully filled electrons. But notice here, class, the energy gap between them is very low. Energy gap is less than 3 electron volt. This is considered as low energy gap. So when this amount of energy is needed, then electrons move and conduct. Like silicon and germanium, these two values you have to remember at any cost: 1.1 electron volt and 0.72 electron volt. These values you have to remember because they are asked in the question. So conduction band is empty. This is written at 0 Kelvin this occurs. And valence band is fully filled. Energy gap is small, that is less than 3 electron volt. So silicon is 1.1 electron volt, germanium is 0.72 electron volt. All right, energy gap is very low, less energy gap is present. Now you can differentiate. See, in conductors, conclusion, see class, listen carefully, otherwise I'll ask you questions. In conductors, what happened? In case of conductors, you had conduction band and valence band spaced with each other, or they partly overlapped with each other. One difference is here, they are not overlapping. Secondly, in case of conductors, conduction band had electrons. Notice here, class, conduction band has electrons over here. partly filled electrons in conduction band. In insulators and semiconductors, you do not have conduction band filled. But how will you differentiate insulators and semiconductors? With energy gap. For insulators, any energy gap is quite large, 3 electron volt. For semiconductors, the energy gap is quite low, less than 3 electron volt. These values, please remember, class. If I note down all these points, any difficulty, any query you have, any point you have not understood, let me know. I'll clarify it. I hope this band theory is clear to all of you.
Yes, teacher.
What about the others? Okay. Now see class types of semiconductors. Mainly you have two types of semiconductors. Intrinsic semiconductors and extrinsic semiconductors. So pure semiconductors, no, that have only one single atom, the main parent element only involved. Those pure semiconductors are known as intrinsic semiconductors. No any element is added. Fine, they do not have any impurity. Impurity is very, very less. Fine. In case of extrinsic semiconductors, these are impure. Impure means they have certain dopants added, as in some amount of element. Other elements are also mixed with these elements. So you call them as extrinsic. So they are also of two types. One you have is the P-type semiconductors. Secondly, you have is the N-type semiconductors. So before we go into each of these details, no, one basic thing, let me tell you, that will help you to understand all these three types. Yes, this vacancy is whole, this part. See class, let's take the example of silicon. For example, let's take, because here two terms will be used. दो चीजें use only. One is electron and one is hole. So that's what I'm saying. See, let me draw structure. Silicon. So these are the electrons of silicons that are present. All the electrons of silicon are there like this. Now see, these join together, no? The electrons share with each other and that results into formation of covalent bond. It's like electron-electron bond, right? Now see, if you somehow add an electron, you call the electron the negatively charged elements that are present here are the electron. But somehow, let's say this electron has been removed. This is nothing over here. So when electron is not there, there will be positivity. If you remove this electron, somehow you remove this electron. So that will result into positivity. That positive part, which is vacancy of electron, deficiency of electron, where electron is not present, that vacancy, that you call it as hole. So I'll be using the term like holes move, holes get transferred, electrons get transferred, holes do not move. So do not think that holes are some entities, any other physical entities that have their existence. Hole simply means lack of electron, no electron present. But just for our reference, we use the term. Fine. We treat them as positive charges while saying it, while using it. But physically, it has no meaning. It is just electrons are not present. So that is a hole. So hole and electrons, these two terms we'll be using. Then let's start with then intrinsic semiconductors, or do one thing, note it down. Do one thing, note down these 2 points. Then we'll start with at least intrinsic, let's do intrinsic semiconductors. C class for intrinsic semiconductors. Now let's take the example of silicon only. Silicon atoms are present. So it will be having one electron and the second electron. This is not 2 electrons or 4 electrons that are present. This is showing the sharing of one electron. This is showing sharing of another electron. These are single electrons only. Understood, class? Like this. The way I draw it, no, like this. Same thing I have represented instead of a single line. Like this. Now see, intrinsic semiconductors, as I have told you, these are pure semiconductors. Now, if the bond breaks between these are electron, this way, the bond between the electron breaks. So what will happen? If the bond breaks, the electrons will conduct electricity. Right, class? The electrons will conduct electricity. So in this case, what will happen? See, number of electrons that are getting excited, that will leave. Like this electron, this will leave. Here a positive hole will be created, hole will be present. Here now a hole will be present. So number of electrons excited, let me write it. Number of electrons excited is equal to number of holes created. Basically, though, how are these holes and electrons created? You increase the temperature. This leads to increase in thermal energy. Because of this thermal energy, the electrons may break. They break among themselves. And now the electrons that are available, the electron which we call as the free electron, this is available for electricity. Electricity you can say, or conductivity you can say. So number of electrons is equal to number of holes in case of intrinsic semiconductor, number of atoms in an intrinsic semiconductor. All right. This is intrinsic semiconductor. Now, if you want to draw the conduction band and valence band here, how will you draw it? See, for intrinsic semiconductors. This is the conduction band. Here you have the valence band. So these are semiconductors. So this band gap between them will be very low. This band gap will be from them will be very low. So when silicon's energy gap becomes 1.1 electron volt and germanium's electron energy gap becomes 0.72 electron volt, then these electrons from the valence band get free and go into the conduction band for conduction to occur. But what are the limitations of these? That number of holes and number of electrons that are created are very small. 10 to the power minus 6, 10 to the power 6 in 1 meter cube. You have such small. You can see 10 to the power 6 is such a small number. And energy gap is very large. Right, that is the limitation of intrinsic semiconductor. Energy gap is less than 3 electron volt. So high energy band is needed. So this is what is meant by intrinsic semiconductors. There is no addition of any atom. Silicon was there, so you can see silicon atoms everywhere. Number of electrons that will be leaving will be equal to number of holes that will be created, because hole is just vacancy of electron. Fine. So that's why we have intrinsic semiconductors as pure semiconductors. Note it down. Let me know when you're done.